And here's the stacked rapid sand filter. And again, there's all these multiple paths. And let's think about that for a second. In this case, let's look at these 4 inlet pipes. What fraction of the filter flow goes through each pipe? Or how many layers does each pipe serve? So we can do some quick checking and look, this top one, it only serves 1 layer, but the second inlet, it serves a layer above and a layer below. And so that's how many layers each of those pipes is serving. And that in itself causes us a problem, because if we use the same size pipes for all of these inlets and outlets, which layers will tend to get the most flow? Well, there's got to be some head loss in the piping system. And so if we have twice as much flow going, or we'd like twice as much flow to be going through the middle pipes compared with the outer pipes are going to end up getting a little bit more water than what we had hoped. They'll get maybe, instead of 1/6 of the water, maybe they'll get, I don't know, 1/5 of the water. They'll get a little bit extra water, and there'll be more water flowing through this bottom layer and this top layer, because it was easier for the water to go through the pipes because there was less flow in those pipes. So that's a problem. So that was all like context. Like, man, there are all these places where there's flow division, and there's differences in the flow paths. So how can we make water split equally between several paths in a manifold? So at the bottom here, I've got this blue manifold pipe. You can think of this being an inlet into the bottom of a clarifier, but for some reason it's upside down. I don't know, it's pointed up, but it's a pipe that's sitting inside a tank. I'm not showing what this section, what the left-hand side is connected to. There's an elbow there and it's going up and it's connected to something, okay? But so we're dumping water into this tank. And you should think of my entire PowerPoint slide as being underwater, okay? And I'm gonna be dumping water, forcing water into this pipe. And I'd like the ports 1 through N, to each have the same flow. And to make it easy to fabricate, I want all of those ports, the orifices, and I want their diameters to all be exactly the same. But my question to you is, well, okay, I'd like QP1 over QPN, the flow out of port 1 divided by the flow out of port N, to equal 1. That's what I'd like to have happen. There's a reason why I'll never get that, but I'd like you to think about, what could I do to get closer to having that ratio equal 1, meaning I get uniform flow? So should I increase the diameter of the orifices to make the flow more equal between ports, or should I decrease the diameter of the orifices to make the flow more equal? You should decrease the diameter. And I will try to explain why that matters and why that makes sense. And to understand why decreasing the diameter helps, we have to first understand the source of the problem. Like, why is it that the flow isn't uniform between these ports? And if we can understand why the flow isn't uniform, we'll then be able to understand why decreasing the diameter of the ports actually helps. So here are 4 strategies that we could try to solve this problem of getting equal flow. We could make all the paths identical. So if you have a way that you can make all the paths identical, that's an interesting option, because that completely solves this problem. If the paths are identical, you have no problem. You could add custom head loss to each path. That's complicated. You could increase the identical head loss in all paths to make the differences insignificant. I wanted to read that like 3 times. But if there is some unintended difference in head loss in the different paths, if you make the head loss in all of the paths intentionally larger, that could dominate the small difference that's there. And we actually use that technique. You could reduce the head loss. You could use a large diameter pipe for the manifold. And let's go to why. So some physics. And we're going to do an aside first, which is just because it's fun. It's fun for me, at least, because I get to ask you another question that is troubling. And by the way, the stuff that we're talking about today is not something that is just easily intuitive. So how do you know which way water will flow in a pipe? And by this all connects in the end, okay? So here's two hypotheses that you, I'm sure, have heard. Water flows downhill, so goes from higher elevation to lower elevation. Or you might have heard that water flows from high pressure to low pressure. Yes? You've heard one of those or both of those? Huh. Well, I'm going to prove that they're wrong. So let's take a swimming pool and let's drop a pipe into the swimming pool. All right. Now take your favorite explanation for which way water flows in a pipe. If you believe that water flows from high elevation to low elevation, then it's going to flow in that direction. And if you believe that water flows from high pressure to low pressure, pressure goes down as you go down in the pool. So if we go from high pressure to low pressure, that means it's going to flow up. And what do you know is actually happening? If I drop a pipe in a pool, does water flow in the pipe? Good. You all know that perpetual motion is not a thing. If that ever changes, we're suddenly rich, right? Because we install a turbine, we generate electricity, and we solve the world's energy problems. But in the meantime, it means that the rule of water flows from high pressure to low pressure, or water flows from high elevation to low elevation, isn't simple enough. Those are too simple. We need a better explanation. So the actual explanation is water flows from high piezometric head to low piezometric head. And so let's try that. So I will make the case in the next slide. I'm going to use a new symbol, PSI, and I'm going to stumble over it, psi, that is the sum of the pressure divided by rho g plus the elevation. So here's another fun thing. Now we've added a sloped pipe, that same slope pipe we had before, but we've connected to another tank up above, and we have our swimming pool. And the first thing we want to do is we want to figure out what the piezometric head is at 0.1. So let's try it. So we have piezometric head is pressure divided by rho g plus z. If we defined z equals 0 at the water surface of this tank, which is just a really convenient datum, and if we say that the pressure, that atmospheric pressure, is also our datum, then we can say that the pressure at the surface of the tank is 0. And now, what happens as we come down? P1 is equal to negative rho g times z1. And because pressure equals rho gh, and that height difference is negative z1. So that means that piezometric head is 0. Piezometric head in a lake is 0, which all that means is that if you take a straw out to, let's see, you're not that close to Lake Ontario, but no, it's Erie. Which is above you? It's Erie. Okay, if you would go up to Lake Erie and stick a straw into it, how high would the water rise in the straw? the water would rise to the surface of the lake. And that defines your datum of if your z equals 0 point is the surface of your lake, that's a representation that piezometric head is 0. If you want to go into real detail, you would have to think extra hard about what happens when you have density differences inside the lake. So for right now, we're ignoring that just to make our lives easy, okay? We assume a lake full of water that's all the same temperature like it is right about now. Okay, so the piezometric head is 0 everywhere in the lake, which means that there's nothing moving the water around except the wind that's pushing it on the surface, but there's no pressure or piezometric head differences driving water flow in the lake. And if we go inside this pipe that I have closed off, but it has water at a higher level, what is the piezometric head there? So its water surface is H higher than the lake's, and so its piezometric head is actually equal to H. So the piezometric head inside this pipe is H, and the piezometric head in the swimming pool is 0. And that means that if I drill a hole anywhere along this manifold, this pipe, water will come out because water goes from high piezometric head to low piezometric head. Am I convincing you? So piezometric head at 2 is H. And if I now put orifices in the side of that tube, water will flow out of all those orifices. And the reason it flows out is because there's this piezometric head difference and it all looks great. So what sets H? Oh, what sets H? Can you think about that? What is determining H in this? Like, what determines how deep the water is in that tank, in the upper tank? That pressure is, can you tell what would happen if I increase the rate of droplets going into this tank? What happens? Like right now, I just have a droplet a second going in. What if I increase the rate of droplets going in? What's going to happen to H? Okay, it's gonna spill over because I didn't have the tank at H drawn any taller. But if I increase the flow, H has got to increase. What's causing all that head loss? What's causing H? It's the head loss going through the pipe and coming out the orifices. So H is set by the flow rate and by the head loss through those orifices. Okay, let's write the energy equation. So there's our friend, the energy equation. The piezometric head is the pressure and the elevation difference, or the elevations. So there's a piezometric head on each side of the energy equation. And we can look at what's causing a difference in the piezometric head. So now we're going one layer deeper. We're realizing, oh, maybe there's another reason why the piezometric head changes inside a pipe. And it turns out, unfortunately, that there is a reason why the piezometric head changes, because look, if we put a control surface at 1 and a control surface at n, the velocity in the manifold pipe is different at those two control surfaces. Up here at 1, there's a lot more water flowing through cross control surface 1 than there is through control surface n. That means V1 is a whole lot higher. And that means that there is a change in piezometric head related to two things, either caused by the change in velocity in that manifold pipe or due to head loss in the manifold pipe. And in a water treatment plant, our pipes are relatively short often. These manifolds are often relatively short, and so head loss ends up being pretty insignificant. And that means there's a change in piezometric head in a manifold because the water is moving and it's changing velocity. And where's piezometric head higher? This is where the surprise pops out. Where is piezometric head highest in that pipe? VM1 is a big number. VMN is a small number. So that means that delta piezometric head is a positive number, which means that piezometric head is actually increasing in the direction of flow. The piezometric head actually gets larger as you go down the pipe because the water inside the pipe is slowing down, and as it's slowing down, some of its kinetic energy is turning into potential energy. This is like the crazy big surprise of manifolds. So did you see what happens? Because water in the pipe is slowing down as it goes down the manifold, the piezometric head is actually increasing, and that means that the last port gets more flow coming out of it than the first port. And I can just about guarantee that if I had given you a question on that one, you would have said that the first port gets the most flow because that's the shortest path. But for the case where head loss in the major losses in the manifold pipe, for the case where that is insignificant, it's the last port that gets the highest flow rate. And I love the fact that I see some puzzled faces because you're like, that can't be right, Monroe. You've got to be pulling our leg. And I'm telling you, I'm as serious as I can be. I'm not pulling your leg. This is actually the way the physics works. If there's significant head loss, that changes the equation. Because remember, I dropped head loss off the equation here. But there often isn't significant head loss in these pipes. So that the change in piezometric head is due to this change in kinetic energy. It's about the kinetic energy term in the energy equation and the fact that there's a change in kinetic energy and it's being converted into potential energy. Because the flow expansion that's effectively happening inside the manifold is happening very, very slowly, it's actually pretty efficient at converting that kinetic energy into potential energy. Remember, if you do a sudden expansion, you lose almost all the kinetic energy. But here we're doing a very gradual expansion as the water is going down this manifold. And the result is that we recover that kinetic energy, turn it into increased potential energy, and the last port gets the highest flow rate. So I want to just show one other place. Oh, let's do this. No, I already told you the answer to this question. The last port has the highest flow rate. So you're going to get it right now, right? The last port has the highest flow rate. And now can you think about why, okay, it's the kinetic energy change in the manifold that's causing us problems. How could you change the design of a manifold so that there's not as much change in kinetic energy in the manifold? Which is the same as asking, how do you reduce the velocity in the manifold? Because if I reduce the velocity, I'm reducing how much kinetic energy there is. So how do I reduce the velocity in a manifold? I make it bigger. So you could solve the problem by making a monstrous manifold. That's one very viable option. And it's one that we always have to play with. And there's always this economic trade-off. The other approach is what if instead I make really tiny orifices? Now I've got lots of head loss through each orifice, and that means that the difference in the pressure, so now the pressure inside the manifold, or the piezometric head inside the manifold, is going to increase a lot. I'm going to have more total piezometric head. So my average piezometric head, my psi m, my average piezometric head is going to be much larger. And the delta piezometric head, assuming I'm keeping the same size manifold, is still the same. But it means that the difference in piezometric head doesn't matter so much because it's a much larger total let me say that again. The difference in piezometric head between inside the manifold and outside the manifold is really big. The difference in piezometric head inside the manifold is tiny. And so that tiny change doesn't matter so much. So we can make the change in piezometric head inside the manifold not be significant by making there be a huge difference between the piezometric head inside the manifold and outside of the manifold. And we can do that by using teeny tiny orifices. So the other solution is just drill the tiniest holes you can make inside this manifold from one end to the other, have the water shooting out of there at 1 kilometer per second, and there will be no difference in flow between those various orifices because the difference in piezometric head inside the manifold is inconsequential. Also, did you see that no matter what we do, we pay for it? We either pay for getting uniform flow by building a big manifold or by using more energy. Sorry, we have to do one of those. And it's always going to be a trade-off there. I want to just end with just show another illustration of where this shows up in the design. And aren't you glad I'm not showing you all these equations? But the equations are there if you want to actually know the math for how do you actually figure out how big a manifold needs to be, okay? But here's another place in the plant where it's a slightly different system, but we have a different kind of a manifold. It's a channel. So the channel that's delivering water to the filters, the water might be flowing in through this end here, and then it's being delivered to both of these filters, and it's flowing across a weir. And now, which filter gets more water? I should have numbered them, but is it the filter that's closest to you or the filter that's further away from you, given that the water is entering from the side that's closest to you? Which filter gets the highest flow rate? So see, intuition tells you that it should be the closest path. The shortest path should get the most flow, but it's wrong. I'm sorry, it's wrong. It's the last filter that gets the most because the water that's flowing in this channel literally piles up at the end of the channel and pushes more water over the weir. The water has more velocity entering the channel. Here's another way to think about it. In order for the water in the channel to slow down, somebody's got to push on it and make it stop. And that somebody is the end wall. The end wall is pushing on the channel. And in order to push on it, the water actually builds up a little bit right at the end of the channel. And so the water level is higher at the end of the channel. The last filter gets the highest flow rate. And so we have to make the channel big so that the velocity in the channel is low. And we have to have a fair amount of head loss over these two weirs so that the change in water depth in the channel doesn't matter. Wow, with that, now that you've been shocked in realizing that the shortest path is not necessarily the way the water will choose to go,